Supersonic cracks. A detailed explanation. Supersonic cracks are a fascinating phenomenon in the field of fracture mechanics, where a crack propagates through a material at speeds greater than the speed of sound in that material. This behavior, while rare and specific to certain conditions, has profound implications in materials science, earthquake dynamics, and structural failure analysis. Background and fundamentals. What is a crack? A crack is a discontinuity or fracture in a material. It forms under stress when the material's cohesive forces are overcome. 1. Subsonic cracks. In most cases, cracks propagate at speeds slower than the material's sound speed, Cs, limited by energy dissipation and stress wave interactions. 2. Supersonic cracks. Under certain conditions, the crack tip accelerates beyond the material's shear wave velocity, Cs, or compressional wave velocity, Cp. Wave speeds in materials. In solids, two key wave speeds dictate the propagation of stress waves. Shear wave velocity, Cs equals sqrt mu, ρ, mu, shear modulus. Rho, material density. Compressional wave velocity, Cp equals sqrt lambda plus 2 mu, ρ, lambda. Lamè's first parameter. Cp, Cs. Supersonic cracks occur when the crack tip velocity, Vc, exceeds Cs or, in rare cases, Cp. Conditions for supersonic cracks. Supersonic cracks are not typical and require 1. Material properties. Brittle materials with high elastic moduli and low plasticity are more likely to exhibit supersonic cracks. Examples: glass, ceramics, and some polymers. 2. Loading conditions. High strain rates and dynamic loads. Examples: explosions, impacts, or rapid stress release. 3. Geometrical factors. Pre-existing flaws or sharp stress concentrators. Specific crack orientations relative to stress fields. Physics of supersonic crack propagation. Energy considerations. Crack propagation requires energy to 1. Overcome material cohesion, fracture energy, g. 2. Create new surfaces at the crack tip. In supersonic cracks, 1. The energy release rate, g, exceeds the fracture toughness, gc. 2. The dynamic stresses at the crack tip become localized due to shock wave formation. Stress wave interactions. 1. At subsonic speeds, Vc. 2. At supersonic speeds, Vc, Cs, stress waves lag behind the crack tip, forming a Mach cone similar to a sonic boom. The stress intensity at the crack tip increases sharply, which can destabilize the material. Dynamic fracture mechanics. The equation governing crack tip velocity, Vc, is influenced by 1. The material's elastic constants. 2. The stress intensity factor, K. 3. The energy release rate, G. For supersonic cracks, modifications to classical theories, like Griffith's theory, are needed to account for nonlinear effects and wave mechanics. Types of supersonic cracks. A. Shear supersonic cracks. 1. Crack propagates with velocity exceeding the shear wave speed, Cs. 2. Observed in dynamic shear failure or earthquake faults. 3. Example: ruptures along faults during earthquakes. B. Intersonic cracks. 1. Velocity between Cs and Cp. 2. Common in Mode 2, in plane shear, fractures. 3. Example: polymer or composite materials under dynamic shear loading. C. Transonic cracks. 1. Velocity near or slightly above Cp. 2. Extremely rare due to the instability of stress fields at these speeds. Experimental observation. Supersonic cracks are difficult to observe directly due to their transient nature. However, advanced experimental techniques have provided insights. 1. High-speed cameras capture crack dynamics in brittle materials under high-speed loading. Example: glass shattering under explosion. 2. Stress wave analysis Detect stress waves using piezoelectric sensors or strain gauges. Measure stress intensity and crack velocities. 3. Numerical simulations. Finite element models simulate stress distribution and wave propagation. Examples: simulations of earthquake fault dynamics. Applications and implications. A. Earthquake dynamics. 1. Supersonic cracks, called supershear ruptures, occur in earthquake faults, producing high-velocity seismic waves. 2. Consequences: amplified ground motion near faults. Enhanced destruction in populated areas. Material failure analysis. 1. Understanding supersonic cracks helps design materials resistant to dynamic failure. 2. Applications: aerospace, impact resistance in aircraft materials. Construction, seismic-resistant structures. Shock physics. 1. Supersonic cracks are relevant in studying explosive fragmentation and shock wave interactions. 2. Example: military and defense applications. Challenges and open questions. Despite advancements, challenges remain in understanding supersonic cracks. 1. Theoretical limitations: extending fracture mechanics to account for nonlinear stress fields in wave interactions. 2. Material behavior: determining why some materials resist supersonic cracks. 3. Real-world scenarios: linking laboratory-scale observations to large-scale phenomena like earthquakes. Conclusion: supersonic cracks are a complex and fascinating phenomenon where material failure interacts with wave mechanics. They bridge the gap between fracture mechanics, dynamic systems, and material science, with far-reaching implications in fields like geophysics and structural engineering. Further research is crucial to fully understand their behavior and mitigate their destructive effects.